Great. Next up, we have Elaine giving us a talk about the implementability of global protocols. Take it away. And you need a microphone.
Thanks. Hi, everyone. My name is Elaine, and I'll be telling you about a network-parametric solution to the implementability problem for global protocols. So let me start by introducing global protocols using the example of a task delegation protocol. So we have here 3 participants, a server and 2 workers, and the goal is for the server to delegate a task to these 2 workers. Among these 2 workers, one of them is diligent, so upon receiving a workload, it will immediately service the workload and send it back to the server. The other worker, however, is lazier, so it may send back the entire assigned workload, or it may choose to delegate part or all of its workload to the diligent worker, worker 2, in which case each of these 2 workers sends back half of the workload. Even in the case that the server decides a priori to split the workload between these 2 workers, the diligent worker will, of course, return it right away, but the lazy worker may still choose to assign its portion of the workload to the diligent worker and have it return it to the server. So global protocols go by a number of names. They were first introduced in the form of high-level message sequence charts, whose visual formalism we're using here, and they're also featured prominently in contemporary programming language frameworks like session types and choreographic programs. The essential features that are common to all global protocols are the following. The first is that the behavior of all participants is specified jointly from a bird's eye view. So in this message sequence chart diagram, the vertical lines describe each of the 3 participants, the server and the 2 workers. Secondly, the sending and receiving of a message is specified atomically. So the horizontal arrows that connect the server and worker 1 in this case, labeled by a payload, describes the atomic and instantaneous exchange of this message half between them. Finally, the control flow in a global protocol is also global. So in this protocol, the various branching points correspond to decisions made by either the server or worker 1 as to whether to further delegate work. Global protocols inspire a top-down verification methodology in which they are used as blueprints from which to synthesize correct by construction distributed implementations. So we desire to synthesize one local implementation for each participant in the protocol so that when they are run in a distributed system, they are free from deadlocks and conform to the global specification exactly. As with any synthesis problem, one needs to first answer the question of realizability, which in our setting asks whether the assumptions that we made in the global protocol abstraction, namely that there are no message channels, so messages cannot be reordered or delayed, they are instantaneously sent and received. And also there is a global coordinator that ensures that all of the participants together follow the same branches. Realizability asks whether these assumptions are realistic to make in a distributed setting, in which the only way that participants can gain information about the global system is by sending and receiving messages. In fact, our running example contains sources of non-implementability. So let's look at just 2 of these branches in the protocol. In the first one, server sends worker 1 the full workload. Worker 1 delegates half to worker 2 and completes half of it itself. In the right branch here, server splits the workload between worker 1 and worker 2, but worker 1 nonetheless decides to delegate its portion to worker 2. So worker 2 first services server's half and then services worker 1's delegated half. So these are 2 scenarios that are described from a global point of view, but let's have a look at what really happens in a distributed setting. So in a distributed setting, server first sends the full message to worker 1 receives it, and now worker 1 proceeds to send a message to worker 2. So worker 2 has this half message that is available for it to receive in its channel. Now let's look at the second scenario. So again, server sends a half message to worker 1 receives it, and now both server and worker 1 want to send half messages to worker 2. These 2 sends are independent, so the network can reorder as well as arbitrarily delay them. In this case, the network has first delivered the message from worker 1, and the message from the server is still in flight here. from the perspective of worker 2, these two branches are identical. The only thing that worker 2 can observe is that there is a half message from worker 1 that is available in its channel for it to receive. However, depending on which of the two branches the other two participants took, worker 2 is supposed to perform different actions. So in the left branch, worker 2 is supposed to immediately reply with a half message, whereas in the right branch, worker 2 is supposed to wait to receive first the message half from server, service that, and then service the message from worker 1. And performing the opposite action in each of the branches will lead to either a deadlock or a violation of the global protocol. For that reason, this global protocol is not implementable. So we could repair this protocol by changing the message payload in the left branch from half to delegate. So this way, when worker 2 receives a delegate message, it knows that it should immediately reply, whereas when it receives a half, it should wait. Unfortunately, this is not a universal repair. And to see this, let's take a closer look at just the right branch. So in the right branch, we have two messages that are both in flight, two half messages to worker 2. And the network can reorder them, so it schedules the message from worker 1 first, and then the message from server. Now, worker 2 knows that it is supposed to service the server's half first, and then worker 1. Whether it is actually able to do so depends on the particulars of how these two messages that are in flight are buffered. In particular, if both messages are buffered in the same FIFO queue, a la mailbox communication, even though worker 2 knows the order in which it's supposed to receive and process these messages, it is unable to do so due to network reordering. So this will lead to a deadlock in the system. Hopefully, these examples make it clear that the question of implementability should be considered to be parametric in a choice of network or on a set of network assumptions. And our goal in this work was to propose a single characterization of implementability and a proof of its preciseness that reasons about all different asynchronous networks at the same time. So the first question that we need to answer is, what exactly is an asynchronous network? And the literature's partial answer to this question is that, well, there are a lot of different models of asynchronous communication. So to tour you through some of the most common models, we have mailbox, as we've seen, in which all incoming messages from different senders are buffered into a single FIFO queue for the receiver. This is implemented in actor-based programming languages like Elixir and Erlang, and decision problems like synchronizability have been studied specifically for this model. The dual of mailbox is senderbox, in which all outgoing messages from a participant are buffered into the same FIFO queue. This can be found in work-stealing paradigms in parallel programming. Another common network model is what we call a mono bag. So here, all messages are buffered into a single multi-set that all participants have access to, and this is commonly assumed by consensus protocols. By and large, the most common and popular communication model is peer-to-peer FIFO. So here, we have 2 channels per pair of participants in the protocol. This is ubiquitous in theoretical results from concurrency theory, as well as commonly assumed in verification frameworks. So we classify networks along 2 dimensions. The first is a communication topology that maps ordered pairs of sender and receiver to buffer data structures. The second dimension talks about what the buffer data structure is. In particular, it's characterized by partial insert and remove operations. So this is what is containing the messages. And with that, our distributed implementation model is a set of local implementations, one for each participant, that is connected and communicating across a network architecture, defined in terms of these 2 components. With this, we are able to give a formal language semantics to network architectures. And we do so by removing the influence of local implementations on the set of behaviors that the system is able to execute, by setting each local implementation to be the universally accepting language. So now the only behaviors that can be executed are entirely dependent on the network architecture, the order in which it allows to send and receive messages. So this way, a network we define as a formal language. It's the set of finite and infinite words that are executable by the universal communicating system under a given network architecture. So we have an answer to what an asynchronous network is. Now we want to design this implementability characterization. And our starting point is an existing precise characterization that is specifically for peer-to-peer FIFO communication. In a nutshell, this characterization says that when a participant is in a state of confusion about which of two states it could be in, it is allowed to send a message that is allowed by both states. It is allowed to receive a message that will help it to uniquely distinguish the two states, but it is not allowed to choose between sending or receiving a message if it doesn't know which of the two states it's on. So this was proven to be a equivalent characterization of implementability, and we generalize these conditions in two ways. The first is that the ability to receive a message is highly dependent on the network architecture. So we call the new condition generalized receive coherence that depends on a parameter A, which is the network architecture. We add a fourth condition, which intuitively says that insufficient information is the only cause of possible deadlocks or protocol violations. So in a setting where participants have perfect information, the protocol is not allowed to contain runs that would nonetheless deadlock. And in fact, we saw violations to each of these two new properties. So the first scenario where worker 2 doesn't know whether to reply or to wait is a violation of receive coherence. And the second scenario in which the system deadlocks in spite of worker 2 knowing exactly what to do is a violation of prefix extensibility. So we have our implementability characterization. We need to go back and qualify the asynchronous networks under which this characterization is precise, right? Because it doesn't obviously work for all of them. The way that we do this is we define a set of axioms or channel compliance facts that talk about the network as a formal language. So these are algebraic in nature, and they say if certain words are in the language, then certain other words must also be in the language, and so on. And so with this, we have achieved our goal of having a network-parametric characterization. So we prove that for any network architecture that satisfies these algebraic axioms, our generalized coherence conditions are precise with respect to implementability. This is, however, not a fully satisfying solution. Suppose I wanted to use the framework to target communicating mailbox systems. So what I need to do is I need to prove these channel compliance facts for the mailbox system. And now suppose that I wanted to also target sender box communicating systems. Well, because these are two distinct network architectures, I would need to reprove all of my channel compliance facts. And this is oftentimes non-trivial. We would like to be able to ignore the effect of varying communication topology in determining what networks are instances of our framework. And this is exactly what we do in the final step. So we distill our channel compliance facts down to a set of simple operational axioms that talk only about the buffer data structure. So these describe the insert and remove behavior of buffer data structures. Looking at B1, for example, this says that insertion is a total operation. This immediately rules out bounded channels. Looking at B4, it says that if I can remove from a buffer, then inserting another message doesn't prevent me from being able to remove that message, which immediately rules out priority queues and stacks. But with the same ease, we can conclude that FIFO queues and multisets satisfy all of the aforementioned buffer axioms. So this new methodology says that we prove B1 through B8 once and for all for FIFO queues and multisets. And from this, we can obtain that mailbox and sender box and monobox peer-to-peer FIFO bag are all instances of the framework without having to establish any new proof obligations. As a freebie, we also obtain that heterogeneous network architectures that mix the use of FIFO queues and multisets are also instances of our framework. We implemented our decision procedure in an extension of a tool for peer-to-peer FIFO called Sprout. So Sprout additionally takes as input a choice of 5 common homogeneous network architectures. It implements a sound and complete reduction to MuCLP and discharges the obligations to a state-of-the-art MuCLP solver. We show that Sprout does not sacrifice efficiency despite supporting more network architectures. A more interesting aspect of the evaluation is that by looking at the average verification times of 3 network architectures, we show that these times track the theoretical relationships that we were able to establish among classes of global protocols that are implementable by each of these 3 network architectures. So intuitively, the smaller the set is of implementable global protocols, the more difficult it is and the longer it takes to verify implementability. So that's all that I have for today, and I'm happy to take any questions.
As with before, please come up to the microphone if you have questions. Unlike before, I don't have a runner mic, so you have to come up.
Perhaps this is obvious, but I didn't find it so. It makes sense to me that given proving all of the buffer axioms for FIFO queues and multi-sets, that you would be able to recover the rest of the behavior. But the heterogeneous mix of either the bags and the queues does not seem the fact that you can mix them doesn't seem obvious to me. Especially when you said that if you have to make the decision between receiving a message or replying, that things kind of fall apart. So what is it that is allowing the heterogeneous mixture of different message dispatching models to sort of join up to maintain these properties?
So when we prove the step from basically that the B's imply the F's, right? We are universally quantifying over all possible communication topologies. So what is sort of dispatching this obligation is showing that these data structure assumptions are sufficient to give us these formal language theoretic algebraic axioms.
So that part makes sense, but what is it about the composition of the different, because you have the buffer axioms and you said okay, each of these individually satisfies it. Does that always mean that any composition of those network topologies meets those axioms?
For this set of axioms, yes.
Okay.
And some of these, for example, if you look at the first one, this is like a simple rephrasing of the totality of insert, right? Just phrased as a sort of algebraic property. So it says if W is channel compliant, then you can always append X, which is a send event, and this stays channel compliant. So for some of them, the correspondence is obvious, and for some of them, less so. There isn't sort of a clean mapping.
Hi, excellent talk, thank you. I wonder if you could talk generally about message ordering guarantees in asynchronous, and I know there's an impossibility, but I wonder if your system has considered synchronous checkpointing for causal ordering versus FIFO ordering, and if you could.
Right, so causal ordering is an interesting one that doesn't cleanly fit into our framework because it is not sort of architectural. So you can't purely define it as the cross product of some choice of data structure and topology. As for asynchronous, or in general, what I can say, for example, we don't support message dropping, only reordering and delay. So that also rules out a large class of asynchronous models in general.
We have time for about one more question while we wait for the next speaker to set up. I have one last question, if that's all right. So we often see in network architectures that their bounded queues are a bit fundamental. That even if we modeled something as FIFO, fundamentally there is a bounded buffer, and that the way we get unboundedness is by applying back pressure. Does this violate the assumption, or is sort of this back pressure based theoretically bounded, but in practice not, wind up working out for your model?
So our framework does not support bounded queues in any way, because that would violate the totality of insert. However, if you had a communicating system with bounded channels, this would be a finite state system. So this sort of suggests a different set of techniques to solve the problem.
Great, let's thank the speaker one last time.